Welcome back. We want to talk about deactivating groups now. In the previous video, we saw how nitrogen, carbon, oxygen, and halogens are orthopara directors. Nitrogen, oxygen, for example, have those lone pairs next to the aromatic ring that cause it to be an electron donating group, which activates the aromatic ring and makes it more reactive than benzene. Now, deactivating groups are going to be caused by electron withdrawing groups. So I'm abbreviating EWG as electron withdrawing groups. Okay? Now, an electron withdrawing group obviously withdraws electrons from the aromatic ring, and it decreases the electron density there in the ring, making it less nucleophilic, and it slows the reaction down relative to benzene. So let's draw those two reactions again side by side. So we have a benzene, which just has a hydrogen here at the top, okay? And that's going to attack an electrophile in the usual way because of the pi cloud, or the molecular orbital that describes all those electrons in the ring, right? And so that's going to have a certain reactivity. Now, if you have a electron withdrawing group directly attached to the benzene ring, what that does is it decreases the pi electrons. So I'm going to draw these pi bonds like as finely as I can. Maybe I'll even switch to a smaller line here. So these pi bonds don't appear as bold here on the screen, and the reason why is because the electron withdrawing group is pulling those electrons away from the pi bond. So there's less electron density available, and when the aromatic ring that's substituted here tries to attack the electrophile, it's going to have a harder time doing so because it's not as electron rich, okay? And we like to say that it's deactivated, all right? And it's going to be slower. So this is going to be fast, this is going to be slower. When we say something's deactivated, we say it's less reactive, okay, compared to benzene. So what kind of groups will deactivate an aromatic ring? The basic idea here is that anything that has a pi bond adjacent to the so the first category are pi bonding withdrawing, okay? So anything that has a pi bond adjacent to the aromatic ring is going to be an electron withdrawing group, okay? So you have a whole bunch of those. Ketones, aldehydes. Okay, so Z can be anything. You can have an aldehyde, for example. It could be a ketone or carboxylic acid. So let's draw acetophenone here as an example. Now don't forget your heteroatoms. It could be sulfonic acid, okay? So basically, we're just looking for a pi bond, okay? So here's a pi bond, here's a pi bond, here's a pi bond, okay? So and Z oftentimes is a heteroatom like oxygen or nitrogen or sulfur or whatever. Nitro is a very strong electron withdrawing group as well. Let's include that here. So nitro group is somewhat awkward to draw because of all these formal charges there. But again, don't worry too much about that. Just focus in on this pi bond, okay? So whenever you have a pi bond right next to the aromatic ring, it's going to withdraw the electrons from the aromatic ring. Let me show you why with acetophenone as an example, okay? Now, if I want to draw resonance structures for acetophenone, yes, I could just swirl the electrons around the benzene ring there. But we want to focus on here is the electron withdrawing effect of this oxygen, okay? So again, that's a pi bond, And pi bonds can always be involved in resonance delocalization. Okay. Now this is not a very good resonance structure because we've lost the octet on carbon, we have less pi bonding, and we have charge separation. But that positive charge is right next door to the benzene ring, right? So we can draw additional resonance structures that delocalize that not so good positive charge all around the ring in different carbons, okay? So one of the places you can delocalize it is to the ortho carbon. Okay. We can also delocalize again to the paracarbon. Okay, so the paracarbon is going to have a positive formal charge there. Okay, and the third possible structure here is going to be this one here. So, and then there's the last one where I mentioned you can just move the double bonds around the benzene ring. So we've got several different resonance structures here, and you'll notice that the +1 formal charge, aside from being at the benzylic carbon, is always located at the 2 ortho carbons or the paracarbon. But what I want you to realize here is that we are removing electrons from the benzene ring. You can see, in contrast to the electron donating groups that place a negative charge in the ring, these electron withdrawing groups all place positive charge within the ring, and that by definition makes it less nucleophilic. Okay? So if we drew the resonance hybrid of this molecule here, we could draw a partial pi bond there. Yeah, so we could draw a delta minus here. There's going to be delta plus at the 2 ortho positions and the para position of acetophenone. And so you'll note here that the phenyl ring has less electron density. Okay, you can see how it's delta plus, not delta minus. And so that makes it deactivated. Okay, and acetophenone acts as an electron withdrawing group, and we don't really need to think about the resonance there. We're just drawing a dipole saying that it's pulling electrons away from the aromatic ring, so it reacts slower. Okay, so this would react slower in an electrophilic aromatic bromination, for example. Okay, now we memorized that no chops, right? Nitrogen, oxygen, carbon, and halogen are all ortho para directors. Now it turns out that every single electron withdrawing group is going to be a meta director. I did forget to point out the second category of your electron withdrawing groups, and those are sigma bonding electron withdrawing groups. If you have a molecule that has a very electronegative group attached, okay, this right here, I know we memorized no chops. If there's a carbon there, it has to be electron donating. But look at these 3 fluorines. There are 3 fluorines here that are very electronegative, and so it creates a CF3 group. The trifluoromethyl group is an electron withdrawing group. We can't draw resonance structures to show how electrons are being pulled out to the fluorines, but we can use dipole arrows, much like showing the acidity effects of electronegative elements on carboxylic acids, for example. Another category or an example of this that I can think of is an ammonium. Okay. And so, for example, if we protonate aniline, we get this aniline protonated species. And this one here, there are no lone pairs on the nitrogen, and this is an electron withdrawing group. Why? Because the nitrogen has a positive charge. Electrons are attracted to positive charge, so the electrons are being drawn out of the aromatic ring. So I'll just draw a little dipole arrow showing that. So these two are weak electron withdrawing groups, okay? So those are two things to look out for. All the electron withdrawing groups, doesn't matter what kind they are going to be metadirectors, okay? Now, the Klein textbooks jumps into all these reactions explaining how it's a metadirector. I'll do that in the next couple videos, okay? But for now, just remember, electron withdrawing groups are if you have a pi bond next to the aromatic ring, a trifluoromethyl, or a protonated, something or other right next to the aromatic ring, and those will deactivate the aromatic ring by withdrawing electrons away from the aromatic ring, making them react more slowly, okay? Let's do a couple review problems now. So the question here is, which ring will be more reactive? Toward an electrophilic aromatic substitution. Okay. So you need to come back to your ideas that if you have an electron donating group, these are going to be more reactive. Okay. And we've talked about what those are. Nitrogen with a lone pair, oxygen with a lone pair, carbon like a methyl group or something like that. If you have an electron withdrawing group, and we talked about what those were, they're going to be less reactive, okay? So we have two rings. There's one molecule, but there's two rings, and we need to figure out which one's more activated, okay? So in this top molecule, we have oxygen with lone pairs adjacent to the phenyl ring on the left, and that's going to be the more activated ring. The ketone, or the ester, the carbon-oxygen pi bond part of the ester right here is an electron withdrawing group for the phenyl ring on the right, okay? So this molecule is activated on the left, and it's deactivated on the right because of this interesting functional group that resides between the two, okay? This next molecule as well, we have a weak activator. That's an R group, okay, which is an weakly electron donating group. But what we want to focus on is this one here with the lone pairs. That definitely is a very strong electron donating group. It's a very strong activator. So again, this ring on the left is more active because of the lone pairs. So oxygen with lone pairs is a stronger activator than just a carbon group, okay? So it's not just does something activate or not, there's varying degrees of their abilities to activate the ring, okay? In the next video, we'll find out about halogens.